Good morning, everyone. I'm Deep Sankar Pandey, a PhD student at Rochester Institute of Technology. Today, I will be presenting our work on uncertainty over meta-learning for few-shot classification using the evidential deep learning. Uh, this talk will mostly focus on our work from multidimensional belief quantification for level-efficient meta-learning. I will be using a lot of references from these two works from ICML 2017 and NeurIPS 2018. If we look at the current state-of-the-art deep learning models, then they have achieved impressive performance in many computer vision and natural language processing tasks. But those deep learning models require large level training datasets to achieve good performance. Many real-world problems are limited data problems with limited level data. For example, many problems in medical diagnosis or rare species classification or healthcare are limited data problems where the deep learning models fail to perform reasonably. We humans, we can learn quickly from few examples easily. For an example, take this three-class classification problem where we have three classes, a bird class, a jellyfish class, and a dog class. After knowing these three classes, we can easily identify that this image belongs to the red dog class. This is a challenging problem for deep learning models, and this problem has been formulated as a few-shot learning problem. The key goal is to learn based on limited number of samples, and the few-shot classification problem has been formulated as n-way k-shot classification problem. Here I show a 5-way two-shot classification problem. What this means is that the model uh, has to classify between the 5 different classes, and for each of the classes, the model has two labeled examples. Using this knowledge, the model has to learn to become a accurate 5-class classifier. For example, uh, the model may be given these 10 examples, that is the support set information. The model can learn from these examples, and the model will be evaluated on new unseen examples from these classes that make the query set. The model will be evaluated on the query set performance. To address this few-shot learning problem, different meta-learning approaches have been developed. The meta-learning models aim to gain the meta-knowledge, the prior knowledge during the training phase, so that the model can perform well on new unseen tasks during the evaluation. As the model learns on a large number of tasks during the training phase, it acquires the meta-knowledge, and that helps the model perform well on new unseen tasks. In meta-learning, the model learns in two levels. In the meta level, where the model learns the task general knowledge that is shared across all the tasks, and in the task level, where the model learns task-specific knowledge to perform well on the given task. Here, I show the meta-learning setup to better describe the meta-learning. So there are two phases, the meta-training phase and the meta-test phase. During meta-training phase, the model trains on large number of the training tasks. Each task consists of the support set and the query set, and during the meta-training, both the support set and the query set information is available to the model. The model uses the knowledge of the support set and the query set of large number of training tasks to learn the task shared meta-knowledge. During the meta-testing phase, the model is evaluated on the test task. The model uses the knowledge, the meta-knowledge and the support set information, and This model is evaluated on the query set. The query set performance on the test task measures the generalization performance of the meta-learning models. Using this setup, many meta-learning models have been developed. Among them, the model-agnostic meta-learning model has shown promising results. The model abbreviated as MAML, this model aims to learn good initialization that is shared across all the tasks such that the model can easily adapt to new tasks using few labeled data points of the support set and just using few steps of gradient descent. The key idea is during meta training, we learn a good initialization. From this good initialization, the model can quickly adapt to each of the tasks using the task-specific knowledge. Uh, uh, the few-shot learning problem, the problem of learning from limited number of samples, it has two key challenges. First, since we aim to learn from limited number of labeled samples, the model's predictions on all samples cannot always be trusted. Many of the predictions will be uncertain. The problem itself inherently introduces the uncertainty, and we require uncertainty awareness in the meta-learning models. Second, to acquire the meta-knowledge, the model needs to train on a large number of tasks. But many of the tasks may not contribute at all to the meta-knowledge. We require efficient task selection method to select the most informative task so that the model can be efficient in acquiring the meta-knowledge. We aim to address these two key challenges. Towards uncertainty awareness, we extend ideas from the evidential deep learning framework to the meta-learning setting that leads to a computationally efficient, uncertainty-aware meta-learning model. With the uncertainty information, we introduce a novel task selection method to decide the most informative tasks. We label only those most informative tasks and carry out the meta training. Before I go into our model, I will first describe the evidential deep learning framework. If we look at standard classification models, uh, these models use neural network to parameterize the multinomial distribution. This is the likelihood distribution. The input is passed through the neural network. The neural network parameterizes this distribution, and uh, the argmax functions are used to do the classification. In such uh, classification models, there is no mechanism for fine-grained uncertainty quantification. The evidential classification models improve upon such standard classification models. In the evidential setting, uh, these models introduce a prior distribution over the likelihood distribution. For classification, uh, one idea is to introduce a higher order Dirichlet prior distribution over uh, the multinomial distribution for likelihood and train the neural network to output the parameter of this Dirichlet distribution. This higher order Dirichlet distribution enables fine-grained uncertainty quantification in the evidential classification models. Uh, to better understand uh, the uncertainty quantification capability of this evidential deep learning model, here I present some illustrative example. Uh, in the evidential models, we pass the input X through the neural network. The neural network outputs are transformed by some activation function. This is a non-negative activation function, and it could be the ReLU function, the soft plus function, or the exponential function that transforms the output of the neural network into the evidence. This evidence is then transformed into the parameters of this Dirichlet distribution. And the Dirichlet distribution enables the fine-grained uncertainties. For instance, consider a input X for which the model is confident and it's not confused. Uh, the model can express a confident prediction without any confusion using a sharply peaked Dirichlet distribution centered at one of the corners of the simplex. Here, the model can output high evidence for one of the classes and low evidence for all of the classes. This leads to the sharply peaked distribution and low vacuity and no dissonance. What this vacuity means is the vacuity is the measure of lack of confidence in the prediction, and low vacuity means that the model is confident. So in this way, the model can express a confident prediction on which it is not confused. If there is an input that the model has never seen and the model wants to say, I have never seen this sample, I don't know, don't trust me, the model can basically output low evidence for all of the classes. This leads to a flat Dirichlet distribution with very high vacuity and no dissonance. What this high vacuity means is that the model is saying, I don't know, uh, I have no knowledge, and this prediction cannot be trusted. Uh, for an input on which the model is confident but is confused to which class the sample belongs to, the model can output high evidence for multiple classes. This leads to a sharply peaked Dirichlet distribution that is centered on the simplex. This leads to low vacuity and high dissonance. The dissonance measures the confusion of the model that is very high. So here the model is confident but is confused among the different classes. Finally, for cases on which the model is uh, not confident and is super confused, it can output high vacuity and high dissonance. Basically, the model outputs low evidence for all the classes, but there is a lot of uh, confusion among the evidence leading to high vacuity and dissonance. In this way, the model can express the different fine-grained uncertainties. Uh, in the evidential models, uh, the model can express its opinion using the multidimensional beliefs. There are three key multidimensional beliefs. First is the vacuous belief or the vacuity. This measures the lack of confidence of the model. Low vacuity means that the model is confident. For instance, in the first case, the model has high evidence for all the classes, leading to a sharply peaked distribution and a low vacuity. Here, the model is confident. If you look at the second case, there is low evidence for all the classes that leads to a flat Dirichlet distribution and a very high vacuity. Here the model is not confident at all. The second belief is the conflicting belief that is measured through dissonance, and this measures the level of confusion of the model. In the first case, even though the model is confident, it is confused among different classes. That leads to very high dissonance. In the second case, the model is not confused among different classes and the dissonance is low. Finally, we have the incorrect belief that just measures the incorrectness of the model. But to know whether the model is incorrect or correct, we need the ground truth information. Once we have the ground truth information, we can just measure the sum of the beliefs for all classes other than the ground truth to measure the incorrect belief. In our work, we analyze these multidimensional beliefs and theoretically show that for any given sample, this incorrect belief is lower bounded by half of the conflicting belief. What this means is that we can estimate a part of the incorrect belief using the conflicting belief. We require the ground truth information to know the incorrect belief, uh, but to measure the conflicting belief, we do not require the ground truth, and this can give an estimate of the incorrect belief. The proof of this theorem is presented in our paper. Uh, with this evidential deep learning framework, we next look at the training for such evidential models. The standard classification models, they are trained using the cross-entropy laws. The evidential classification models introduce a prior distribution over the likelihood and train using evidential laws. Uh, in addition to these laws, they introduce some incorrect evidence regularizations uh, to minimize the evidence for classes other than the ground truth class. These models are trained with the evidential laws. We extend such evidential deep learning frameworks to the meta-learning model. Um, we extend using the mammal model as our base model, and we replace the mammal model with this evidential model. We replace the cross-entropy laws with the evidential laws and train the model. We train the model such that after learning from few examples from the task, that is, after adopting on the support set, uh, the model can show good performance and also output the uncertainty information on new examples. This is our units model, that is a evidential meta-learning model for few sort classification. Uh, Next, we look at the results from this uncertainty-aware meta-learning model. If we look at the overall generalization performance of our model, then our model achieves comparable generalization performance across all the datasets and settings. So the evidential model does not lose in terms of the generalization performance. But the key advantage comes in terms of uncertainty. The proposed model has the uncertainty, and that can be used for OD detection. Here we show the results from one of the experiments that over the omniglot dataset. For this task, after learning on the support set, the model can predict well on the query set and is accurate with low uncertainty. If we rotate these query set samples and evaluated on the rotated query set samples, then with the increase of the rotation, the model's predictions start to become incorrect as indicated by the red color. Correspondingly, the model's vacuity also increases. That is, the model starts to say, I don't know, as the samples become more OD. This illustrates the uh, potential of our model for OD detection. This is also shown by the model when we evaluate using completely different samples from the MNIST. Uh, the model has never seen the MNIST images, and for these images, the model outputs the high vacuity, indicating its lack of confidence on these predictions. Uh, so next, we can also use the uncertainty information for task selection. The key motivation for task selection can be seen through these two tasks. Both the tasks have the same support set, but uh, these tasks have different query set. If we consider the first task, then after learning from the support set, the model's uh, prediction on the query set is correct. Moreover, if we look at the uncertainties, the vacuous belief and the conflicting belief both are low, leading to average low vacuous belief and the low conflicting belief. What this means is that the model is confident and is not confused on its predictions. Moreover, since the prediction is already accurate, learning from such tasks may not contribute to the meta-knowledge. The model is already accurate, it's confident, and it's not confused. If we consider the task 2, after learning on this support set, many of the predictions on this query set are wrong. Uh, there is high vacuous belief and there is a lot of conflicting belief. The model's predictions on some of the samples are correct, but since the vacuous belief is high, such predictions cannot be trusted. The model may have been accurate just because of random guessing. If we look at the overall task level vacuous belief and the conflicting belief, both are high, indicating that the model uh, does not know and it's confused. Uh, Training on such tasks is expected to lead to better meta-learning models. So we propose to consider tasks with high vacuous belief and high conflicting belief, and we only label the such task. We do not consider such task and avoid labeling such task for meta training. More specifically, we introduce a task selection criteria that considers both the vacuous belief and the conflicting belief to determine the informativeness. We introduce a weighting parameter that is dynamically adjusted to determine the informativeness. During the initial training phase, we want the model to acquire the new knowledge. That is, we want to focus more on the vacuous belief. As the model acquires knowledge, we want to focus any acquired incorrect knowledge. So we gradually uh, decrease the lambda value as the training progresses so that the model can consider both these for the task informativeness. We use these to rank the task and select the most informative task, label those tasks, and train the meta-learning model. If we look at the performance of our model with task selection, then it improves over the model without task selection. Basically, our uncertainty guided task selection leads to improvement over the model without the task selection, and it saves over the labeling costs as well. Next, we can also use the uncertainty information to improve the performance. We can use the uncertainty to rank the predictions and consider the predictions on which the model is most confident. If you look at the model's predictions on the most confident predictions, the accuracy is significantly higher, meaning that the uncertainty information is accurate and useful as the model's prediction on the most confident predictions are significantly higher. So in summary, we extend the evidential deep learning framework to the meta-learning setting to develop effective uncertainty-aware meta-learning models. The proposed framework does not introduce any additional computational overhead and leads to a lot of benefits due to the uncertainty. Moreover, the uncertainty can be used to introduce the novel task selection mechanism. So this is all. Thank you for your audience. The code for the proposed work can be found in this link. And if you have any questions or confusions, please feel free to reach out to us at the email or our lab website. Thank you.